here. All right. And what I'm going to do, I'm going to go through a couple of these monohybrids, and then I will show you how to set up the dihybrid because people have a lot of questions about that. I would also suggest doing that worksheet, the monohybrid cross worksheet, because I think it does a really good exam. It shows you the way the questions are going to be worded on the test, and they're a little bit different and they're a little trappier. So one thing is if you have two heterozygotes, no matter once you get really good at doing this and you do this a whole lot, you'll start to see that you're always going to have this. Two heterozygotes crossed is always going to give you a 3-to-1 ratio for 3-to-1 phenotypic ratio, or for the trait, because that's the phenotype is what's actually expressed, okay? It doesn't matter if you're looking at flower color or tall versus short. You're always going to have, if you notice, a phenotypic ratio of 3-to-1, okay? Or a genotypic ratio of 1-to-2-to-1. Get used to seeing this. Get used to understanding this. Now, you can draw this out. Nobody's asking for you to memorize two heterozygotes give you a 3-to-1 or a 1-to-2-to-1 ratio. But this is something that after you draw these enough, you're going to know. On your test, you're probably just given, like, if you have two heterozygotes, what would the ratio, two plants that are heterozygotes, what is the ratio that the flowers would be purple, assuming that purple is dominant? So then you would just have to kind of draw this out, okay? Or at this point, you might just know. Now, here's a question that we went over in the last lecture. How many gametes will be produced for the following allele arrangement? So this is remembering that 2 times n, and n is the number of heterozygotes. Now, it's easy enough when you've got this, but it's still a little difficult. But as we move forward in some of these, you're getting a lot of combinations, and this is kind of what you're going to see on your test. So it's worth memorizing this equation that basically the number of different gametes that could be produced, you can figure out. This is by going 2 times n, and n is the number of heterozygotes. So let's just look at this. How many heterozygotes are in number 1? And you know what? You might want to pause and figure all of these out right now, because I'm not going to stop, but you might want to pause. Answer, how many different gametes will be produced, okay, if you have these different allele combinations. And then go ahead and unpause it when you're done, and I'm about to go through the answers. All right, so these, you have 2 heterozygotes. Does everybody see that? So to do that equation, you would have 2 to the power of 2 right here, okay? And that equals, that's pretty easy, 4, right? Now this one is a little bit trickier, and oh my Lord, my horrible math scores are going to be exposed here because I'm not going to be able to answer this. But we have 1 heterozygote right here, 2, that's a heterozygote, and 3. Does everybody see that? So we have 2 to the power of 3, which means it's 2 times 2 times 2. So that's going to be, if I did my math right, 8. Okay, so 2 to the 3rd equals 8, okay? Again, we didn't count C because that's not a heterozygote. And if that makes sense, the only allele combination, you don't get a different allele combination because they're 2 capital C's. All right, now let's look at this last one. You have 1, 2, 3, 4, 5, 6. 6 different heterozygotes. Am I right? Let's recount it. 1, because big M, little n, big N, little n, so that's 2. Big O, little o, that's 3. This one doesn't count. This one doesn't count. Big R, little r counts. Little s doesn't count. Big T, little t, and big Q, little q. So we have 2 to the 6th power. That would be your answer. Okay. if you have any questions, feel free to email me and hopefully I can help you. But this is definitely a much easier way to figure this out. All right. And here are the answers. And I already wrote out the different gametes for you for these two so that you could see. You can imagine how cumbersome this would be if you were trying to do a test, especially something like this. You can kind of look through these and make sure that you're good to go. All right, these are two more questions I want to run through. So if you want to pause it, I would suggest doing that so that you can answer them, but I'm going to go ahead and answer them. If two plants are crossed, resulting in offspring with a 3-to-1 ratio for a particular trait, what does this suggest? Remember how I kind of warned you? You just kind of are going to draw these Punnett squares enough. That should be a trigger for you. Oh, that must mean they're heterozygotes. Both mom and dad are heterozygotes for the trait. So that is your answer. Okay? Now here's another question that is worded in that weird kind of test format way. Dr. Smith's parents have normal hearing. However, Dr. Smith has an inherited form of deafness. Deafness is a recessive trait that is associated with the abnormal allele D, or little d, right? The normal allele at this locus associated with normal hearing would be capital D, or dominant, okay? What are the possible genotypes that Mr. Smith's parents could have? So what you're looking for in this answer is what Dr. Smith, would have to have inherited two little d's. So both mom and dad have to have a little d in their genotype. But it says that both parents have normal hearing. So that means that neither one of them could be the recessive, because in order to exhibit this trait, you'll have two recessive, so you'd be a little d, and neither one of them are deaf. So that means that both parents have to be hiding a little d underneath their phenotype, okay? But they can't neither one of the parents could be big D, because that means that Dr. Smith was the mailman baby, because he had to inherit a little d from both parents. Because in order to have this trait, it is a recessive trait, so you have to have two little d's. So both parents would have to look like this. Big D, little d. And if you need to draw out a Punnett square to prove that to yourself, then do that. Now is not the time for the ego to believe you don't need to draw Punnett squares. Drawing Punnett squares is how you practice and you get so darn good at predicting genotypes, because you've drawn so many. So this shows you where this is where you get Dr. Smith showing up. And that's where people say, oh my goodness, he's the mailman child. But he really wasn't. All right, I'm going to pause and I will come back. Oh, actually, let me do this one too. In garden peas, the allele for tall plants is dominant over the allele for short plants. A true breeding tall plant is crossed with a short plant. Out of 20 offspring, how many should be tall? Well, let's look at some of the vocab here. True breeding means that if something is true breeding, all it can give is that allele. This is a definition we went over earlier in one of the earlier lectures in this unit. True breeding means that there isn't a recessive allele hiding underneath. You could have a true breeding, a homozygous recessive, or a true breeding homozygous dominant. Either way means true breeding. It can only give that trait, or it can only give that gene. Okay, so it's another way of saying homozygous. A true breeding tall plant is crossed with a short plant. Now, up here it says tall is dominant over short. Out of 20 offspring, how many should be tall? Well, we know true breeding, tall means you've got to have 2 big T's, is crossed with a short plant. Short is recessive. So you've got to cross something like this going on. Big T, little t, little t. Okay? And so when you draw your Punnett square, and maybe some of you won't have to draw your Punnett square for this, but if you need to draw it, again, now is not the time to have the ego to think you're too good for Punnett squares. You would get something like this, and what you would find is that all of the offspring are going to be tall, aren't they? Because that dominant T, the big capital T, makes everybody tall. So out of 20, how many should be tall? 100%, or all 20. Okay? All right. So I am going to go ahead and pause, and I will come back and we'll talk about probability a little bit.